morning, sir. I am Saitya from EEE department. Today, AAT topic is about calibration of marine pressure sensor with a combination of temperature and pressure. Introduction to marine pressure sensor. Understanding the foundation of oceanographic sensing. Purpose, pur- Purpose of marine pressure sensor used to measure the pressure exerted by the water column above, enabling depth calculation and monitoring of ocean dynamics. Common application employed in underwater vehicles, sea-based observation, offshore drilling platforms, and tidal monitoring system. Sensor technologies include physio, physioresistive, capacitive, resonant quad, and mesemi-based pressure transducer tail rod for high pressure environment. Importance in oceanography supports studies in ocean circulation, sea level rises, tsunamis detections, and marine ecosystem behavior. Principle of operation: how marine pressure sensor functions underwater. Hydrostatic pressure concept. Sensors calculate the depth by measuring pressure from the water column above, increasing linearly with depth. Transduction mechanism. Pressure induces a mechanical deformation that converted into an electrical signal by piezoresistive or capacitive elements. Signal conditions, amplification, temperature, compensation, and filtering are applied to enhance accuracy and usability. Data output typically provide analog voltage or digital data integrated with data loggers or telemetry system. Why calibration is crucial in marine environment, ensuring accuracy in dynamic oceanic conditions. Environmental variability. Pressure sensor faces fluctuation in temperature, salinity, and biofouling, all of which impacts accuracy. Pressure drift and sensor hanging. Over time, sensor can drift from their original calibration, necessitating periodic recalibration. Application sensitivity. Applications such as tsunami detection or climate monitoring demand sub-millbar precision. Compliance standards. Calibration ensures compliance with ISO, NIST, and oceanographic quality control protocols. Environmental factors affecting sensor accuracy. Temperature fluctuations, temperature changes affect sensor electronics and material expansion, impacting measurement accuracy. Salinity variation. Salinity influences the density of seawater, alternating hydrostatic pressure reading. Biofilling and sediment deposition. Accumulation of biological material of sediments on sensors can obstruct pressure ports or affect diaphragm response. Dynamic ocean motion. Waves, tides, and current introduce short-term pressure variations and sensor noise. Interdependency of temperature and pressure. The thermomechanical coupling in marine sensor performance. Thermal expansion affects sensor diaphragm and internal components expand with temperature alternating pressure readings. Thermistor-driven compensation. Sensor often incorporate thermistor to correct temperature data in real time based on temperature. Depth temperature profile. Temperature varies with depth. Thermocline requiring depth aware compensation models. Nonlinear coupling. Pressure and temperature effects are not independent. Calibration must consider their interaction. Conventional calibration techniques, laboratory methods, and in-situ flows. Static pressure chamber calibration. Sensors are subjected to known pressures in a lab chamber. Comparison output against a certified standard. Dead weight tester. Use of unknown masses to integrate previous static pressure ensures traceability of to national standard. Temperature cycling test. Sensors are exposed to control temperature variation to quantity, thermal drift compensation, field cross calibration. Sensors are co-deployed with reference instrumentation to compare real-time data in operational conditions. Limitations of traditional approach: signal point calibration inaccuracy, laboratory versus field conditions, sensor drift over time, lack of dynamic compensation. Traditional method often relies on few calibration points, insufficient nonlinear pressure temperature effect. Lab environment cannot replicate ocean turbulence, salinity, and biofilling pressures. Sensor drift over time calibration may degrade over long deployment due to material fatigue and environmental exposure. Many sensors lack real-time algorithm to adapt to changing temperature pressure states. Combined temperature and pressure calibration concept. Dual domain calibration strategy, multi-dimensional response surface, enhanced model fidelity, real-time applications. These are the combined temperature and pressure calibration. Experimental setup and procedure. Pressure simulation chamber, thermocouple environmental, data logging and synchronization, sensor mount and interfaces. Data accumulation and proceeding, transforming sensors output into calibrated measurements, synchronizing sampling, higher resolution data logging, noise filtering, data normalization and interpolation. Mathematical modeling, curve fitting, polynomial regression models, surface fitting techniques, error analysis and residuals, model selection and validation. Calibration algorithm, compensation tool, lookup table, LUTs, polynomial based calibration, machine learning models, errors bounding, and self diagnostics. Results and performance comparison, error reduction metrics, comparison with single factor models, repeatability and drift suppression model, robustness across depth. Challenges and mitigation strategy: biofilling and sensor degradation, environmental variability, long-term stability, logical and cost barriers. Pressure transducer design and material. Mechanical architecture for marine condition. Diaphragm construction. Utilize thin film titanium aster or ceramic membrane for corrosion resistance and pressure sensitivity. Sensing elements integration, piezoresistive strain gauge or capacitive plates embedded on the diaphragm converts deformation to signal. Oil filled isolation, protective oil chamber with elastic seal isolate the sensor electronics from direct water exposure. Packaging for depth rating, housing made of anodized aluminum or pressure rated stainless steel allows operation smoothly. Mathematical base of hydrostatic pressure calculation, fundamental equations, density variability, dynamic pressure effect, calibration implications. Digital signal processing technique for sensor output, filtering transient disturb- disturbance, real-time smoothing, spectral decomposition, outerline detection and correction. Case study: deep sync deployment calibration analysis, deployment parameters, environmental dynamic calibration verification, data impact. Validation with oceanographic reference instrument, benchmarking sensor accuracy using trusted standard reference instrumentation calibration compared against Seabreed SBE39 and Para Scientific DG Quanta sensor, lab and field validation cross verification performed in controlled chamber and OpenSea co-deployment strategical agreement reschedule between test sensor and reference typically within plus or minus 0.01 of full-scale readings. Calibration traceability ensures NISTs and SI units conformity via channel reference and measurements. Conclusion and future works towards next generation marine sensor calibration, integration of AI and edge computing, real-time learning and adaptive calibration using onboard AI for dynamic marine environment, miniaturization and power efficiency, development of ultra-power calibration system for long-term autonomous deployment, interoperability and standardization push to word common protocol to enable cross-platform sensor calibration and validation, cloud-based remote calibration, leveraging IoT and satellite connectivity for on-fly model updates and analytics. Thank you.